Hello and welcome. Eamonn Darcy is my name. I'm the founder and operator of QEQA, the Quantum Education Centre of West Australia. And we're already up to video lesson 8 on quantum teleportation. Quantum teleportation, it sounds so Star Trekky, and that's because it is. It's amazing. Let me say one thing straight away. Physicists believe that we're going to be able to send a quantum particle from the Earth to an orbiting spacecraft. Now, that's amazing when you think about it. So a quantum particle being teleported 200,000 kilometers instantly. And we mean instantly. It is unbelievable. When do you think we'll be able to do that? In 10 years? In 50 years? In 100 years? Or we'll never be able to do it? Pause for a second and get your answer sorted. Okay, welcome back. Well, the answer is we've already done it. In 2016, quantum scientists in China teleported a quantum particle from a laboratory in Tibet to an orbiting spacecraft called Micius. That's M-I-C-I-U-S if you want to Google it. So isn't it absolutely amazing? Believe me, something as complex as quantum teleportation, if you attended these 8 lessons just for 10 minutes each, you will be able to grasp the concept of what's happening. Now, obviously, teleportation is involved. All the mathematics is very complex and the logistics and the practicalities. But I want you to be able to, by attending all of these lessons, I think you will understand and grasp the concept and how it's actually done. But let's just recap. Lesson 1, superposition. A quantum particle can be in multiple states at once. It's not just on and off. It's got an amazing property that it can be in multiple states, and computers can reference to these multiple states. So a classical digital supercomputer that we have now can only access 2 states, on or off, which it calls 0 or 1. It can't call it minus 300 squared over the cube root of pi. It can only call it 0 and 1. But a quantum computer can refer to multiple states, and it can use multiple complex numbers. So it really is quite amazing. Lesson 2, we got in touch with entanglement, and that's another wonderful, amazing force where 2 quantum particles can be separated by distance, yet they are and act as one. So that really is unbelievable, and that allows us to have a string of qubits. We could have, 100 qubits, and by changing one of them, we can change all 100. So it's amazing. I then spoke about the interpretations, because this is important. What is really going on? And of course, we really don't know what's going on. So at the moment, we're interpreting what's happening. There's no question that it's happening. Superposition and entanglement have been proven thousands of times. It's happening, but what's happening? And we have interpretations like the Copenhagen, we have cubism, pilot wave, de Broglie pilot wave, but and also the many worlds interpretation, which gets a lot of press because it's so out there. Linear algebra, just the basics of multiplying matrices together and getting over the fact that a matrix and matrices can, using advanced linear algebra, they can mathematically replicate superposition, basically. So a quantum computer is just one quantum particle in superposition, and we can map to all different superpositions in the one quantum particle. It's amazing. And the block sphere, which we engaged with on lesson 5, the block sphere is the visual representation. So whereas you've got, like, for all computers, non-quantum computers, classical digital supercomputers, they all only have a light switch on, off. That's it. But as we know now, the quantum computer, the qubit, is in superposition, so it needs a lot more explaining, and we do that through the block sphere, which is fantastic. The quantum gates are merely matrices that affect the block sphere so that we can account for the different superpositions on the block sphere. So the quantum gates allow us to navigate around the block sphere. Then we had quantum games. Wasn't that amazing? The Paris Merman, which is a game that you can very, very quickly realize you can't win all the time. In fact, if you play 24 times, you've got a 1 in 1,000 chance of winning. Of winning every game. The whole 24 games is 1 in 1,000. So you can imagine if you carry on, the odds are totally against you. Yet if you use a quantum strategy and you use quantum qubits to play the game, you can win this game every time for infinity. For an infinite number of games, you will always win. And you win because of another strange property of quantum particles called quantum contextuality, which means that if you measure that square by the row or by the column, it will give different answers. And then it's fundamentally different. It's amazing. But that was a fantastic one. And today is quantum teleportation. And I'm hoping by the previous 7 lessons, you'll be able to understand this. It is involved, but honestly, you're going to understand it. So let me set my timer and let's go. 10 minutes. Okay, what are we talking about when we say teleportation? So I'll talk about that first, and then I'll go into the process. And you'll be amazed how you'll be able to follow it. So what are we talking about when we say teleportation? So are we talking about it being able to magically move from one place to another through a loophole in the fabric of space-time, through a porthole type thing? No, we're not. Are we talking about every atom of the object is deconstructed and sent to another location and then reconstructed? No, we're not saying that either. But what we are saying is that we will take a quantum particle, we will transport the information to another location, which could be millions and millions of miles away. That's the amazing thing we're talking about. And you're going to understand it. We spoke about quantum gates in lesson 6, I think it was. And believe it or not, the actual quantum algorithm, the quantum gates that you need to understand are only for the most basic gates you learn in lesson 1. The Hadamard, the C0, the Z gate, and the X gate. By learning those 4 gates is going to be enough for you to understand the process of quantum teleportation. How amazing is that? And behind each of these gates, remember, I like to impress this upon you, are the matrices, and they are very straightforward matrices. And then behind these matrices is the physical microwave pulses that change the superposition. Okay, so let's move on. Quantum teleportation, the process, it's the quantum information of the subatomic particle that's actually transported. And here it is. Now, I won't go through it particularly. I'll just tell you conceptually what's happening. Remember, the horizontal lines are merely qubits. And you can see the top, middle, and bottom line, qubits. The top one is the actual particle we want to teleport. And the bottom 2 are actually what we call, they're entangled. They're called Bell states, which is maximally entangled. But they're entangled, and that's all you need to know. So in a laboratory somewhere, someone created this Bell state between two subatomic particles, the entanglement that we've already spoken about. They sent one to Alice and one to Bob, and they're still entangled. So the top two qubits are in Alice's laboratory, the bottom one is in Bob's, but they each have one of these particles that are entangled. And then look, you only apply a couple of gates, and amazingly, the exact quantum particle that Alice has goes all the way to Bob. Really is amazing. Look, I don't want to get too much into the mathematics, but that equation at the top merely means psi, which is the wave function, equals alpha 0 plus beta 1. And alpha and beta are merely probabilities. They're called complex amplitudes because they can be complex numbers. So whereas you've got, when you've got a coin, you flip it, the probability is 50%, it'll be heads or 0. 50%, it will be 1 or tails. Now, alpha is merely the probability that a quantum bit, if you flip it, will be 0, and beta is the probability that it's going to be 1. But instead of just being 50%, it can be the strange -1 over the square root of pi to the 18th over the cubed root of 11 over 6. Alpha and beta can be anything, and that's why a quantum particle can do so much. But the amazing thing is, remember, in the double slit, you can't measure them. If you try to measure them, they instantly disappear. They collapse, the collapse of the wave function. So somehow Alice has to send her wave function, which is psi, which is the combination of alpha and beta. She has to somehow teleport that all the way to Bob, who could be a million miles away. Qubits 2 and 3 are a million miles away from each other, but they're entangled. Now, you can't entangle qubits that are millions of miles. You can't apply a C-naught, to two qubits that are a million miles apart. But in her own laboratory, she can entangle the top qubit, which is qubit 1. She can entangle it with her part of the entangled pair. That's really the way it's done. So you've got the qubits 1, 2, and 3, and they're represented by, at the moment when they start off, they're all in 0. And you can go through this slide by yourself, or I may do a whole lesson on it later, but I want you to see that it's not really complex. The first set of brackets on the top equation are merely Alice's qubit that she wants to transfer. And then the second bracket here, 1 over square root 2, 0, 0, 1 over square root 2, 1, 1, is merely the Bell pair. So that's the two of the qubits. Qubits 2 and 3 are represented by that Bell pair. You multiply them out, you apply a C-naught gate, you do all the mathematics, which is honestly very basic. You're just multiplying it out. And then you can see that if you look at the information inside the box, remember what Alice now does is measure her qubit, and she's measuring her qubit that was entangled with Bob. So that's her second qubit. So that's the 0 in the middle, when we say alpha over square root 2, 0, 0, 0. The middle qubit is her second qubit. And the same whenever you see the 3 digits together. So if she measures it and gets a 0, we know that we have the state that we're looking for. And that merely comes through whatever answer you get, you have to apply an X gate in order to get to exactly what we want, which is at the bottom right-hand corner. And that's the duplication, the exact duplication of the original quantum particle that Alice has. And that's basically it. She then has to, though, once she's measured her own qubit, she has to tell Bob whether she got a 0 or 1. So this is very important. There has to be a classical communication between Alice and Bob. She has to somehow say, hey, I collapsed my qubit and I got a 0 or a 1, and then Bob will apply an X gate or a Z gate depending on what he gets told. So there's a little bit of preparation behind the quantum teleportation. You can't just quantum teleport anything from location A to location B. You have to make sure that, first of all, those particles were entangled, and then you have to communicate the result after collapsing one of the entangled particles. So I hope that's not being too complex for you. It's really is, quite simple once you play around with it. And if you ask me in the comments, I'll do a more specialized presentation on the mathematics behind it. So amazingly, Alice originally had a qubit with 2 complex amplitudes, 2 really weird probabilities of being a 0 or a 1. And then by merely supplying 2 classical bits through any electronic communication, and so by merely supplying a classical bit, which is the outcome of a collapse, it somehow, because of quantum entanglement, it somehow passes that information over millions and millions of miles instantly. This is the power of entanglement. I hope you've enjoyed the lesson. The 9th lesson is on quantum cryptography, which uses everything we've learned so far to send security. And one thing I will say is that for the first time ever, mankind has 100% security. It can now produce a code that can never, ever be hacked. Now, that can be a good thing or a bad thing. Please subscribe to the channel, like the video. It really does help. Talk to you next time.